Hello everyone and welcome to today's lecture. We will see the nature of metals, always in the same chapter, informing engineering materials from the elements. So a material with its atoms held together by a sea of electrons, and in chemistry a metal can be defined as an element with a valence of 1, 2 or 3. We have here atoms and here are electrons. So in properties we have good conductivity, malleability, opacity and ability to be strengthened, and loading can cause atomic slip due to the nature of the bond. For the nature of metals we have the concept of an electron matrix and how crystalline materials deform, cleave or strengthen, and alloying. So how crystalline materials deform, cleave and strengthen. So metals are not brittle and there is no cleavage. In metals the interatomic bonds are such that rather than causing cleavage, loading can cause atomic slip. And atoms rearrange to accommodate any deformation or dislocation is a primary mechanism. So dislocation is the crystal imperfection, and these are the regions of severe atomic misfit. These are some illustrations of moving dislocation in the crystalline material here, and this is the slip plane and this is the slip step. So this is an example of a slip step that is produced when the dislocation reaches a free surface. These are some other illustrations. We have here the deformation. We have here the shear stress, and the crystal array is here. So this is the slip plane, and also this is the shear stress. So to deform this crystalline array, all the bonds must be broken and reformed at once, and this requires high energy. And also deforming a crystal in this way is analogous to dragging a long carpet along a floor. We have here also another demonstration. So the edge dislocation moves along the slip plane in response to the stress, and same thing to deform a crystalline array with dislocations. Only one row of bonds is broken and reformed at once, requiring less energy than the example above. And deforming a crystal in this manner is analogous to pushing a raised bump in a long carpet along a floor, and this requires also a lower energy way of moving a carpet by distance, and this is the distance of deformation. So where do these locations came from? By the way, crystal mismatch in solidification, and there is also an external stress, I mean here plastic deformation. We have also crystal mismatch by phase transformation, and we have the atomic mismatch in alloying. So when metals deform by dislocation motion, the more barriers dislocations meet, the stronger the metal. And we have here also, it's called metal strengthening. This is an example of solid solution strengthening. So here we have the extra half plane of atom and a dislocation trying to move through the metal structure. We have here also the impurity atoms form barrier to motion of A. And solid solution, I mean alloys. This is a large atoms. For mechanical working or metal strengthening, this is a multiplication dislocation, and this is an interaction with grain boundaries. So we have here the before mechanical working and the after mechanical working. So the after mechanical working, we have the grain boundary, and we have here the dislocation, we have here the distorted lattice. This is another example of precipitation hardening. I mean alloying elements. You have here impurity atoms in solution, and you have here the heating causes the impurity atoms to precipitate and form a barrier to the motion of A. So we've seen metal strengthening, and it's also called the dispersion, and it's a fine particle addition. Here is an example. We have the quench hardening. So this is a face-centered cubic structure, and this is the additional carbon that dissolves into structure. And here are the iron atoms and the carbon atoms. The heating to high temperature, that goes to a rapid cooling. So this is a room temperature with body-centered cubic structure, and this is a room temperature with a body-centered tetragonal structure. And it's an example of quench hardening. And for those who don't understand its meaning, it's all about trapping of solute atoms into lattice by heat treatment. So we have here the strengthening iron by alloying with the carbon by cold work by quench hardening, and the significant effect of alloying and quench hardening. We have many things of metal strengthening, for example, solid solution, mechanical working, precipitation hardening, and quench hardening, as we saw, and we have the dispersion as well.